Okay, we will continue our discussion with the numerical methods. Now, so far we have talked about the numerical methods for boundary value problem, linear boundary value problem, nonlinears, and partial differential equation, that is the heat transport equations. Now, when you have a advection diffusion equation, so that means a equation like this, this is the general transport equation, because already we have seen that transport equations are governed by both advection and diffusion. So, a equation like this, del u del t plus u del u del x equal to say mu del 2 u del x 2. So, this is the one we call as unsteady term, and this one is the convective term or advective terms. Convective term due to the transport velocity as u, and this is the diffusion term. So, this is a differential equation, partial differential equation to be precise. Now, this partial differential equation is nonlinear PDE. If I neglect these convective terms, so this is basically the parabolic partial differential equation, which we have already discussed about how to solve this. But if we do not have, we cannot neglect. So, that means, if this term, this u del x is significant, so that means the advective transport is not very negligible. Normally, advection is referred to the heat transfer situation. So, here we can call as a convective transport. So, this convective transport is not negligible. So, this equation in a whole is called the Burger's equation. Now, this Burger's equation is very famous because it has the property of many fluid transport problem, like this is model as a boundary layer situation. So, that means, the momentum equation under boundary layer approximation can be reduced to this form. So, that is why any numerical method can be validated by comparing with the Burger's equation. Another difficulty with that, this equation is in a general we can say it is a parabolic type, but this equation have the hyperbolicity if this diffusion term is negligible. If this term becomes a negligible one, so then in that case this is becoming a hyperbolic one. So, we can pose the boundary conditions in this manner, because this is have both initial and as well as boundary space variables are there. So, boundary conditions, let us talk about the boundary is x is say varying from 0 to some certain length L. So, one boundary is t 0 equal to say some u 0, and u t L is equal to say u 1 for any t greater than equal time started positive, and this is the initial condition. So, u 0 x is f x for 0 less than x less than L. So, this is the initial condition, and two boundary conditions are required, because a second order derivatives are involved for the x and first order for the time. So, if we apply the Crank-Nicolson scheme, so we can write this scheme. So, what you can write is u n plus 1 I minus u n I by delta t plus because this is half, this is u del x at basically Crank-Nicolson scheme is a 2-time level. We are integrating between n plus 1 and n, and using a trapezoidal rule to make the integrations, and this is mu by 2, and this is del to u del x 2 n plus 1 I, and del to u, this is the implicit part and this is the explicit part. So, I grid points is 1 to say n minus 1 and n is greater than equal to 0. Needless to say that we have choose the grid points. Let the grid points are xi equal to what starting is 0. So, this is I delta x and T n equal to n delta t, and I is varying from 0, 1 to capital N, and n is of course positive. So, n greater than equal to 0. Now, obviously, here if I equal to 0 and n, these are the points, are the two boundary points, 0 and n are the two boundary points. So, that is why apart from the two boundary points 0 and n, we need to compute the u for I equal to 1 to n minus 1 for a choice of n between n from 0 onwards, that is from the initial time t equal to 0. Now, if I write the space discretization, space derivative discretization, we get the full form as u n plus 1 I minus u n I by delta t plus half u n plus 1 I u n plus 1 I plus 1 minus u n plus 1 I minus 1, a central difference over here, so to delta x. This is the implicit term, and you have the other. So, what we do is we put all the implicit term to this left side and the explicit term which is known to the right side. So, that means always superscript n plus 1 comes to this, right. So, u n plus 1 I plus 1 minus 2 u n plus 1 I plus u n plus 1 I minus 1 by delta x whole square. This is equal to mu by 2 u n I plus 1 minus 2 u n I plus u n I minus 1 by delta x whole square, and minus half u n I plus 1 minus u n I minus 1 by 2 delta x. So, I equal to 1, 2 up to n minus 1. So, this forms a set of which for n greater than 0. So, for a which forms a set of n minus 1 equations for involving same number of unknowns, involving n minus 1 unknowns u n plus 1 1 to u n plus 1 n minus 1. So, we do not have any. So, that is for a for n greater than equal to 0. For any fixed value of n, we have for any fixed n, because we are going in a forward marching in time. So, that means using the value of the solution at n equal to 0, using the solution at n equal to 0, we are going to n equal to 1, n equal to 2, like this way, next time step onwards. So, we have no difficulty in the constructing the equations for the unknowns, same number of equations, same number of unknowns, but only problem is that it is a nonlinear. Now, to cope with the nonlinear, so what we do is we apply Newton's linearization technique. We apply linearization technique. So, before that let us write that at a fixed value of at a fixed n greater than equal to 0, because we are fixing the time. So, that means from either from first time step 0 to first time step or first to second whatever, but we are fixing a value of n and then we are solving for all I. So, the solutions now will be obtained by the iteratively we apply the Newton linearization iterative technique, which has been discussed before. So, in this iteration what we do iterative technique is that u n plus 1 I at the k plus 1 iteration, which is not known, is approximated as u n plus 1 I at kth iteration plus an error. Let us call this is u n plus 1 I, and where this is the error. So, this is for I equal to 1 to n minus 1. Then we substitute for k greater than equal to 0 is the iteration index. So, what we do is we can take u n plus 1 I 0 in the very beginning is nothing but u n plus 1 u n I, the previous time step solution, that is at the first iteration 0th iteration level. To start with the iteration we can assume this. So, at every iteration we are in the Newton linearization technique, what we do is we approximate the solution u n plus 1 I at the k plus 1 iteration. We made the recurrence relation by this way. This is the error, and we assume that these errors are very small with square and higher orders are negligible. In addition, we have u n plus 1 equal to delta u n plus 1 is 0, because at the two end points, these are the two boundary points where solutions are as solution is known over these 2 points. So, what I do is now we substitute this u n plus 1 I of this form to here and drop all the square and higher order terms of del 2 u n plus 1 I and get a equation which will be linear for delta u n plus 1 I. Now, note that at the k plus 1 iteration already this is computed. So, that means wherever u n plus 1 I k appears is assumed to be a known quantity. It is no longer a unknown. So, say start with k equal to 0. So, that means at first iteration this is already known assumed value. So, that means only unknown is here, and that unknowns are appearing in a linear fashion. Okay. So, that is the beauty of the Newton's linearization technique. So, that is what we did also for the boundary value problem previously. So, substituting u n plus 1 I k plus 1 for all I to the governing equations, to the discretized equation. There is no governing equation and neglecting square and higher orders, of del 2 u n plus 1 I, we get a linear set of, we get a set of linear algebraic equation as, say, let us write in this way: a I delta u n plus 1 I minus 1 plus b I delta u n plus 1 I plus c I delta u n plus 1 I plus 1 equal to d I, where I is varying from 1 to n minus 1. So, this forms a tridiagonal system. So, if I so this set of equations, so let us call the set of n minus 1 linear algebraic equations star can be put in a matrix equation form, as can be expressed as Ax equal to, say, d, where x equal to your all these unknowns, n plus 1 1, u n plus 1 2, etc., delta u n plus 1 n minus 1, and A will be the, A is a n minus 1 cross n minus 1 tridiagonal system. Tridiagonal matrix. So, we can solve this system. So, let us call this is double star. Solve double star to at every iteration to get delta u n plus 1 I for all I. For all I means I equal to 1 to n minus 1. So, this iteration process, so once we get this, then we go back here and modify, that is already obtained, previously obtained value plus the updated value, get these new values, okay, and then proceed further, that is we go for k plus 2 iteration and so on. So, iteration process, iteration converge when we pose this condition as 1 less than equal to I less than n minus 1, delta u n plus 1 I is less than epsilon, which can be of very, very small quantity, something like 10 to the power minus 6 or so. So, this is an repetition, iteration, because iteration means the same process will be repeated few number of times. So, till we get the convergence. Now, here of course, we have assumed that the iteration converge. So, converge means when it can be stopped, that is assumed to be reached a convergence is covered by this condition. So, if we simply say the procedure is that first we discretize this equation to this form, then substitute the u n plus 1 I at the k plus 1 iteration level by this manner, and then reduce this equation to a algebraic equation, linear algebraic equation of this form star, which is the linear equation for delta u i's, at the time level n plus 1. So, that is why n plus 1 is shown, which forms a tridiagonal system A x equal to d. Solve this tridiagonal system and get the x, that is the delta u i's, delta u n plus 1 i's, then go back to this equation, get this, and let us call this equation, we are referring several times. So, let us call this is 1 and this is 2. So, this equation we are calling as equation 2. So, when you get the delta u I and delta u n plus 1 I, substitute here and get the modified value. So, get substitute and obtain u n plus 1 k plus 1 by 2 by using the relation or equation 2. Okay. So, this is the process repeated several number of times. Now, whenever a process is repeated few number of times, then the there is a complication arise that whether the scheme is stable. Stable, as we have stated before, that means if we have a small amount of error is incorporated either through say truncation, either through this round of error and any other manner. So, if that round of error or the error which has been incorporated, if it is magnifies in the subsequent time, so in that case the scheme is said to be unstable. But if we find that the error is reducing with as we proceed with the time, so in that case the scheme is said to be stable. Error is either going down or remain constant. Now, the Crank-Nicolson scheme, as we have stated before, this is Crank-Nicolson scheme, is stable for any choice of delta t delta x, and the truncation error and the order of accuracy is order delta t square delta x square. Now, so we have no difficulties, but thing is we have a situation, we have considered this equation. Now, if nu is very, very small, so in that case then the equation may become unstable if central difference scheme then the numerical solution, not equation, above numerical method, whatever we have discussed before, may become unstable if central difference scheme is used to discretize the derivatives with respect to x. Okay. For a hyperbolic equation, if we use the central difference for x, that is FTCS, forward time and central in x, so that becomes a unstable one. So, that is why say this kind of situations we have to avoid. To avoid that, this is called the upwind scheme. So, in a short form, the upwind scheme will be a more useful for this, and is suggested to cope with the instability. So, in the upwind scheme what it does is, that means u del x at n plus 1 I is taken to be u n plus 1 I u n plus 1 I minus u n plus 1 I minus 1 by delta x if u n I is greater than 0, and this is taken to be u n plus 1 I. So, that means there is a backward difference in x if the flow is in the forward direction, and this is u n plus 1 I plus 1 minus u n plus 1 I by delta x if u n I is less than 0. So, this is the upwind, that is along the direction of the wind. So, when the flow is in the coming forward from the backward direction. So, at this point I, the flow is like this way. Okay. So, this is your u n I. So, you use the points which is backward of yours. So, you are at I. So, you take I minus 1. But when the flow, see this is I and flow is coming like this. So, you use the point, the information from I plus 1. So, that imparts stability provided the if nu is very low. So, that means the dissipation is low. Okay. So, if it is only dominated by the hyperbolic term, that is the advective transport or convection effect is stronger compared to the diffusion effect, then a upwind scheme is suggested. Otherwise, if nu is order 1, then Crank-Nicolson scheme is stable. Now, Crank-Nicolson scheme is stable because there we have used both central difference scheme in the time in the x derivative. Now, before stopping, so far what we have considered is that the space variable is a single variable. So, that means a variable of x only. Now, we can have a situation where the transport equations, we have already seen that you may have a situation like del c del t plus q dot grad c equal to say nu del to c. So, this is again the advection diffusion equation. This is the advection terms, because say fluid velocity and solute transport and others, and this is the diffusion. Now, for simplicity, so q will be an q is the advective velocity, q is already known. So, for simplicity, we first consider this situation, we consider this equation. Now, that means this is nu del to c del x 2 plus del to c del y 2. 2 dimension. We are not, we can have also 3 dimension. Now, I just give one method. Of course, this is the variation of the Crank-Nicolson scheme. Again, this is like a parabolic PD. It is a parabolic PD. Only thing is that it has a higher dimension, that is both x and y are the variables. So, in this case, so what you have is that you want to compute the, let c n I j, this is equal to as c t n x I y j. Okay. So, this is the point we are considering. So, let c n I j be known for some n, for n equal to n, and C n plus 1 I j to obtain. So, this is our task. So, here instead of going C n to C n plus 1 as we do in the Crank-Nicolson scheme, what I do is we go by 2 step. In the step 1, what I do is we obtain that is C n I j to a fictitious time step C n plus half I j. Okay. And so, that means we are moving forward from n to n plus half instead of, so that means T n to T n plus half instead of jumping straight from n to n plus 1, here n plus 1. And the what we do is we discretize the derivatives with respect to say x or y implicitly, and derivatives with respect to y or x explicitly. Okay. So, what basically we are doing is here very simple, C n plus half I j minus C n I j, since it is a half time step. So, delta t by 2 equal to nu, say x is implicitly. So, that means this is the one to be kept at the current time level, and this is the one is explicit, that is previous time level. Okay. And then we use the central difference. So, if we use the central difference, what it will look like? So, this is the one. So, it will look like as, so it will be here. So, it will be quickly, if I write C n plus half I j minus C n I j by delta t by 2 equal to nu C n plus half I. Now, you see, this is the derivative with respect to x. So, that means I is varying, j is fixed. So, I plus 1 j minus 2 C n plus half I j plus C n plus half I minus 1 j by delta x whole square plus C n plus half, sorry, this is explicit. So, C n I j plus 1 minus 2 C n I j plus C n I j minus 1 by delta y whole square. So, because this is in an implicit fashion. Okay. So, and here I and j, I is varying say from 1 to n minus 1, and j is from 1 to m minus 1, whatever the. So, that means I equal to 0 and I equal to n are the boundary, j equal to 0 and j equal to m are the boundary. So, I equal to 0 n and j equal to 0 m are the boundaries. So, a fixed n plus half, which is not to be find out. So, so unknowns are n minus 1 into m minus 1 number of unknowns, and the same number of equations, because if I vary I equal to 1 to n minus 1 and j equal to 1 to m minus 1, so we get the same number of unknowns, and we get a. So, variables are who with superscript n plus half. So, we get this number of equations and this number of unknowns, and important thing is a forms a tridiagonal system. How? For a fixed j. So, that means what I do is, if I keep j fixed and vary I, so this is form a tridiagonal system. Okay. So, I will just say the next step, step 2. So, step 2 what we do, so in that process we got Cn plus half ij. So, here n plus half to n plus 1. So, that means Tn plus half to Tn plus 1. So, again we reverse the direction. So, that means that is why this is the alternating direction, reverse the direction of discretization. That is to say, derivatives, if we have taken x was the implicit, so now it will be derivatives with respect to x or y, here it is explicit, and derivatives with respect to y or x implicit. So, what I get is Cn plus 1 ij minus Cn plus half ij by delta t by 2 equal to, one can write this way, the same manner. So, nu Cn plus half, this is explicit, I plus 1 j minus 2 Cn plus half I j plus Cn plus half I minus 1 j by delta x whole square plus Cn plus 1 I j minus 1 plus Cn plus 1 I j plus Cn plus 1 I j minus 1 by delta y whole square. So, I j, I is from 1 to n minus 1 and j equal to 1 to m minus 1. So, every step we get a, so this is a un plus 1 form I, so equal to T I, where I equal to, for I equal to 1 to n minus 1. So, what I do is here fixed I solve for all j. So, here, so that means you have, if I do in a pictorial form, say these are the grids. So, this is the I is along this direction, I is varying. So, this is I, this is j. So, what we are doing is, these are the boundaries. So, at a fixed value of I, we solve for all j. So, that means now we compute for all j. So, once, so that means we start with from here, so fixed I equal to 1. So, we solve for all j. Once it is done, then I equal to 2, solve for all j, and every time we get a tridiagonal system like this way. AI is a tridiagonal matrix. So, this is the beauty of the ADI scheme, where we get a tridiagonal system at every time step. So, only thing is that we have to repeat this procedure to solve the tridiagonal matrix for n minus 1 times, for depending on the I occurrence. So, that is it, that is the way, and the order of accuracy is again delta t square, delta x square, delta y square, because this is nothing but a variation of the Crank-Nicolson scheme. So, this is a second order accurate in both time and space variables. Okay, so that is it about the numerical scheme. Thank you.